Vincent. Thank you for inviting me as well, and thank you all for coming here. As Vincent said, we're going to talk about environmental footprint of AI and impacts with a S, because there are multiple impacts indeed. And I will focus, it's not only AI, we'll focus on deep learning, which is maybe the focus of today and what data scientists do today. It's mostly deep learning, so focus on that. And we'll discover how to assess environmental impacts and how to reduce them, at least some strategies to do it. I'm Samuel RINCE. I'm an open source contributor at Boavizta, which is a non-profit focusing on making available open source license to data sets, methodologies, and tools for organizations to monitor, track, and evaluate their impact, environmental impact of their IT infrastructures. So it's not focused on AI, it's very the whole scope of ICT, information, communication, and technology. I'm also, my daily job is being a data scientist at Align, where we discover and expose values and opinions about companies, identifying if they are pro or against some topics like deforestation, child labor, corruption, things like that. And we do that thanks to AI and NLP. And not so long ago, I was also in the engineering courses of Central Supélec, and so not so long ago I was in this seat too. And just to give a bit of context of the presentation, hope you've already seen this graph before. It's from the IPCC, from report 6, I guess, showing the different scenario for the global warming and the global temperature rising, depending on the emissions of carbon dioxide, CO2, GHG emissions, not only carbon. And as you see on this graph, we start at 2015. Well, we need to reduce right now emissions, and that's not only for oil companies or mines or the building industry, it's for all industries. So AI is concerned, and AI has to do its job as well. So first, does AI have an environmental impact? If you asked ChatGPT 2 or 3 months ago, it would answer that no, a program doesn't have an impact, and only the hardware, and it's clearly not correlated. They fixed it, so you can ask again the question. It will say, okay, no, maybe not. Let's make sure AI software has an impact first. Your software, whether it's AI or not, always run on hardware, and hardware is always powered by electricity. I think that's clear. Electricity is produced either by renewables, if you're lucky, so solar energy, wind energy, and others. Also, you can have nuclear energy, which is also low carbon, so that's pretty okay. And if you're less lucky, it's fossil fuels, natural gas, coal, etc. And in reality, it's a mix of all of them, because you cannot monitor them the same way. Nuclear, you just give a provision of a quantity of electricity that you can make on a long-term phase. Renewables, you cannot control them. It depends on the sun, on the wind, other factors. And fossil fuels are just there to meet the demand. So we need fossil fuels to meet the demand, the electricity demand in real time. One thing that we can keep track of is the carbon intensity of electricity production, which is basically the mix of all technologies I've showed before. We see in France we're not so bad, thanks to nuclear power. Some other countries in Europe have made other choices, and it results in higher carbon intensity. But what's important to notice, it depends on the location, of course, and also depends on time. And will see an example of that later in the presentation. Then we have the hardware to run your program. Hardware is made of components like CPU, RAM, disk, GPUs for AI, etc. Production of this hardware has also an impact, and it's in fact a big impact. For instance, for a CPU, how we can compute the impact? Well, we can do life cycle assessment and use these methodologies to compute the impact, but it's a very difficult process, and you can do it for one CPU, but if you change the product, you take another CPU from another brand, you kind of need to do everything again. There are 5 steps in LCA. Well, it's around that lines. We go from resource extractions, so it's going into the mines, taking minerals from the ground, processing it, and having like raw materials we can work into the manufacturing phase, where we can produce the CPU, the package you see, the die, so the silicium inside the CPU. Then the transportation from the first factory to maybe the computer factory or the data center where they are going to put the CPU on the server itself directly. Then there is the usage. Obviously, you're producing a CPU, you're going to use it, so it's going to consume electricity. So we can take it into account in the usage. And finally, the end of life. Are we going to just dispose of the CPU in nature? Are we going to recycle it or do something in between? And basically, the LCA is just studying all those steps with regarding all the possible impacts that we can compute for ICT. There is also, of course, the carbon emissions that we all know of. There are AGP, which is ablation of abiotic resources, basically minerals from Earth, to say it's easy. And there are also water consumption, and there are more. I'm not going into the details of that. And so if we just take a global scale, so not only AI, but ICT, information, communication, and technologies. That's basically all your smartphones, computers, TVs, everything that has tech inside. In 2020, it was estimated between 2 and 4% of global carbon emissions in the worldwide. So if you know the numbers, it's more than the civilian aviation worldwide. So it's even a bigger impact than taking the airplane as a civilian. It's still a growing sector. It's estimated by 2025 to double, so between 4 and 8%. And it's impacting in many ways. We talk about carbon, ADP, so natural resources, water, the use of water to produce or to cool down CPUs and hardware, and biodiversity, because if you rely on mines, you have directly an impact on biodiversity because you need a lot of land to extract materials. So in the end, we saw that electricity has an impact, hardware has an impact, so your program running thanks to hardware and electricity has an impact. You can attribute an impact to your software in the end. And the impact is growing. As I said, for ICT, it was estimated that it's going to double by 2025. How AI is doing? Well, it's doing pretty well in terms of models. Here, it's NLP models. I'm more specialized on NLP models, so if you have questions on that, I can answer more easily than computer vision and everything. But we see the same trend everywhere in every sectors. Back in 2012, we had word embeddings models based, like Word2Vec, FastText, Glove. And then it grew with other technologies, the transformer, the attention, like these revolutions happening in 2017. We have the first GPT models, and then we arrive in 2021, where the first version of GPT-3 was released. And you see the scale of parameters. We reached more than 100 billion parameters compared to the small 100 million parameters. It's a big increase for the performance, but also for the impact. Let's take an example of how it is hardware intensive to train a model like GPT-3. I take the example of Bloom, which is basically the same size. GPT-3 is 175, here is 76. For training this model, and it was in France, in Janzé supercomputer, we needed 48 servers equipped with 384 GPUs, data centers GPUs, not the commercial one, the bigger one with a lot of RAM, and all of that for 4 months. So given that you have that hardware, you can only train 3 models like this in a year. So it's pretty massive scale. And if we take a look at GPT-3, comparable to Bloom, it required a huge amount of electricity, and this emitted 552 tons of CO2 equivalent, because we account for GHG emissions. And that's about 256 planes going from Paris to San Francisco, basically an entire year of disconnection, and it's only the go-through, so Paris to San Francisco, it's not Paris to San Francisco, San Francisco to Paris. And it's not over. GPT-4 was announced, and it's going to be not 100 billion, but 100 trillion parameters. So even though there is, we'll see that there's not a correlation directly in between the impact and the size of the model, we can be sure that OpenAI is going to use its cluster of 10,000 GPUs to make that model happen, and that is going to have a big impact on the environment for sure. I was talking about it. I was giving the hint. If we take 3 models, 3 size of models, we have BERT, the base version, not the large version. It was estimated around 0.6 tera. Oh, we're back. Tons of CO2 emissions with a little asterisk because it doesn't account for hardware in this measure, and the others does. T5, which is also a Google model, a little bit bigger, 46 tons, and then GPT-3 that we just saw before. So looking at the numbers, we could say, okay, there's a correlation between the model getting bigger and the impact. Well, in fact, that's wrong. If you take Bloom, which is comparable to GPT-3, it's only 30 tons, only. And this is a very important thing to notice. It's not only the size of the model, but the way you're going to train it, the way you're going to use it, that could influence the final computation of the impact. So it's important to understand how we compute those impacts. And we'll see how to reduce it as well. Let me show you 4 techniques or ways to reduce the impacts, and we'll see in the same time how it's computed. What I call AI sobriety, using pre-trained models, and etc. And we'll see it through the prism of a use case that is sentiment analysis in natural language processing. Basically, it's a very simple task. It's a classical one, at least, in NLP, you have a lot of data sets, EMDB for movie reviews. We have 2 examples there. Amazon reviews on products, or I don't know, TripAdvisors on restaurants. And basically, it's taking a text as an input and giving it a label, positive or negative, relating to the emotion of the text. So we see the first, this film is terrible. It's probably a negative one, and the other one is a positive one. Well, what I call AI sobriety, what it is, it's just going back to the principles of data science, starting with a baseline. Do not just pick the biggest model and say, hopefully it will learn something and it will solve my task. Try to redo some data analysis on your data set. If you have a sentiment analysis, well, you can take a look at the distribution of words. You can have metrics like that to see what your data is made of, so you can make better decisions of how to implement a basic algorithm that will get just above the random, but you still have a baseline. And then you can iterate with more complex methods, machine learning, deep learning. You can get bigger in scale to see what's available to you, what accuracy you can get in the end, but we'll keep in mind that the impact will scale with the models you're going to use. And also, it's important to look at your data in the eyes, because one thing that I can attest for sure in my work, you can take the biggest model you can, and sometimes taking a bigger model, and it always actually work in some sense. But please emphasis on the data pipeline. Like, make sure you filter out your data well. Make sure you present the best data to your model. That's where it's going to perform well. If you present it a text that is clean, you're going to have better accuracy in the end, just by taking time to look at the data and pre-process everything well. And finally, use ensemble modeling. Let me just show you a quick example for our sentiment analysis. You have textual data, and it's a pretty classical task. You see before in the example, it was very easy. You get the sense very quickly if the movie is good or not. If the review is very small, there is less room for noise and less room for ambiguity about do you like the movie or not. So maybe you can take a very small model, like a fast text classifier, which is a word embedding based classifier. Going through the data, it will see all the data, and based on the output of that model, you can choose if you're going to use BERT behind or not. If you have a prediction, we say, okay, it's 1, it's positive, with a very high confidence from the first model. Well, there's a good chance, if you've done pre-processing well and you trained your first model well, that you have the right answer. And then sometimes the first model will get less accurate prediction, and you will see it in the distribution of the weights at the end of the model. Maybe it's a good thing to start with a bigger model just for that piece of data. And if you can filter out 20%, 30, 50% of your data with a very small model at the beginning of your pipeline, well, it's all the data that is not going through BERT, and it's all the data and the computation that you're going to save, thinking that way to build your pipeline. Another one that is maybe very obvious, but I know some downsides usually of doing some research and try to apply it to your case. Just use pre-trained models every time you can, and orient your solutions to use pre-trained models every time you can, because they are there, they are already trained, they already emitted their emissions for the training. So let's not train another model, just use the model that is ready for you. You can do transfer learning, so basically retrain the model on another downstream task, but not from scratch. Or you can fine-tune a model, take your big model, put a head, depending on the task you want to do, so binary classification, multi-class classification, depends, and just train the head of the model, and it will be lighter. You will do very small epochs, steps to train it, and you will not train a whole model. If you think about BERT that we saw just before, it's more and more accessible to train your own BERT with the cloud, but just don't do it. Just use BERT as it is today. So you should avoid training your own model. And for the example I just put before, fast text has already pre-trained word English vectors, so just start from there. And BERT as well, you just can fine-tune on your precise task and not touch the model at all. Another thing that you can do is called workload shifting, and it's not only applied to AI. Anytime you have big computation that is not required to be done in a certain time frame, well, think about workload shifting. Shifting both in location and in time. As we saw just before, some countries will emit more carbon emissions than others. Of course, if you're living in France and you have your server in France, you cannot do much about that. But if you're using the cloud, it's really easy to change the region where your compute is going to happen. So please try to take a look at which country. Just don't take the first default region in your cloud provider. Just take a look at it. Some cloud providers are starting to put numbers on regions and indicators to move workloads, so it can also be automated. But you need to go forward to activate it. It's not by default. And if you're stuck in a country, if you're stuck in France, for instance, well, on a week, we can see that there are variations of carbon intensity. It happens on a week, but it also happens on a year. So in summer, usually carbon emissions are lower than in winter. So if you want to update your models, for instance, you have a task and you need to update to production data, because production data always changes. It's not like a fixed data set. And you need to update your model. Maybe try to, maybe we can create a life cycle of our models and train them in summer instead of training them in winter. Or if you need to work on a smaller time frame, maybe you can take a look at the graph there, which is from RTE, the emissions in real time. So you could say, but maybe it's too late now. We're already at the end of the graph. We missed that peak. In fact, there are APIs that help you to forecast the carbon intensity based on many factors. So you can get an approximation of what's going to be the carbon footprint in most of the countries available for cloud computing, for instance. And you see, and I teased you with this example just before, why two comparable models. There are both decoder-based transformer and transformer-based models. Bloom is just there to copy GPT-3. Sorry. Why is such a difference in carbon footprint in the end? Well, first we used less electricity. That depends on the way you trained it, depends on the hardware. If you're stuck with hardware, you can't very help for that. You're stuck with what you have. But you see on this line, you can clearly influence the final calculation of the carbon footprint, which is just the product of the two, basically, and reduce by a massive amount the carbon emissions just by training your model in France instead of the default region or in the United States or anywhere else. And then we're going to take a look at very like AI-focused techniques. So just before we saw a technique that is applied, you can apply it to any computing. So if you have heavy processing, you can also think about workload shifting. Here it's very focused on AI and deep learning, in fact. One thing that you can do, and most of the things I'm going to present, it's after you have trained your model. It's how you're going to use it in the real life. One thing you can do is quantization. The basic idea is to reduce the precision of the weights of your model. So as you see on the right, you have two graphs, two possible ways to quantize a model. In blue, it's the distribution of weights. So basically, you just count how much weights are in a small portion of the weight values. And you have a beautiful Gaussian-like curve. And the idea is to move and map those weights into the orange bars that are there through quantization. Basically, you just change the space where your weights are mapped. You change the space, you discretize it, and you map all the weights to the closest orange bar on the graph. It's the new weight of the new value of the weight that you're going to use in production. Basically, what you can do is mapping your float 32 version of your weights that you need for training, because you need precision for training, but not for inference. You can map it on float 16, so it's going to reduce the precision of the floats. Or you can even map it on integers. If you do a transformation, you can just encode everything into integers and still use your model, down to binarized neural networks. So that works. You can use like just 0 and 1 in your model, and you still have a good prediction. Of course, there is a catch. You may have a loss of accuracy at the end, so you need to measure that, and you need to test against data sets and make sure you still solve your problem well. But one advantage of this technique is that it doesn't require training or particular training. You can just apply it after training and do this post-training transformation and just get like free reduction of computation. Another way to reduce computation and memory footprint is pruning your networks. Well, I guess you have seen that in your deep learning course, but basically it can be used as a regularization technique, but it's also it can be used to make your neural network sparse and having less computation. You just remove certain parameters, weights or neurons, so you cut connections or you cut neurons. And your representation of your graph is smaller. If your graph is smaller, there's less computation, less memory, so less energy consumed. There's even versions of that that I think are really interesting, where you cut layers, entire layers. Of course, you reconnect them while you're processing inputs. And you can use, for instance, like half the size of a BERT-like model for smaller applications. And it can adapt to the hardware you have. So take a look at pruning. It usually requires more work from you. There are less tools to automate things like that, but you can really benefit from it. Then there is another technique called knowledge distillation. Basically, you take a big model. You can imagine a BERT model on the top as a teacher model, and you're going to train a student model that is smaller, has a very smaller impact and a smaller size, and you're going to train it from the outputs of the bigger model. Basically, the idea is to transfer like the inner knowledge of your big model inside your small model by educating it through the loss of the bigger model and from the ground truth. And finally, about one final step about model compression. It's debatable about if it's compression or not, but I put it there because I think it's the same. It goes in the same box as optimizations for inference. It's compilation. It's different from compiling C code or things like that, but the idea is pretty close. You have frameworks to use your model in production and for inference only that can do a lot of magic on your graph. It can merge nodes. It can remove redundant nodes. Things that you don't need when you're not training, when you're just doing inference. Well, you can use automated tools that are going to look at your graph and just reduce it, cut things that are not used. And you can also apply hardware-specific transformations. Here, it's important to notice that your model is going to get deployed somewhere. It can be on the computer, in the cloud, or whatever. But it's still running on hardware, and there's still a connection to the real world, I would say. And depending if you run it on GPU, on CPU, depending if it's NVIDIA GPU or AMD, and same for processors, Intel, AMD, there are specificities to this hardware that can be used and leveraged to reduce the computation. So take a look at it, and just at the beginning of your project, maybe you should have an idea of where your model is going to get deployed, and then anticipate these modifications. And still, this is for inference. There are some work to use this kind of stuff for training, but it's very not early stage, but very specific. And if we take back our use case of sentiment analysis, very, very quick wins to apply on this use case. It's going from the BERT classifier, you go for dist-BERT. It's already pre-trained. You don't need to train it yourself. Just take it out of the box and you can use it. And it's available in Hugging Face and all the Model Zoo thing you can look online. Your dist-BERT model, nothing can stop you to quantize it. So you reduce the dimension of the parameters inside the model to make it smaller and with less computation. And when you have done that, you've checked that accuracy is still at a good level at each steps. You can finally optimize it for inference in your use case, in your company, in your work, future work, using Onyx Runtime, for instance. There are many more. And just to give you a number, and it's, I guess it's present in the papers, but it's also from my own experiences, you can get up to 5 times a reduction from the computational cost. So it's really an advantage. You reduce the energy and computation, and you also reduce the money you're going to spend in your future cloud provider and things. Less hardware, less money, less computation, less money to use. So it's a double incentive. You reduce emissions, but you also reduce the money you're going to spend on that model. And finally, I want to talk about tracking environmental impacts, what you can do as data scientists to have an idea of, okay, which model should I choose when I'm testing them, how to implement these strategies of energy reduction and environmental impacts reduction in your daily work. Well, I'm sure you've already seen that graph. If not, it's a very classical one. Usually we describe a machine learning project like that. You have the scoping phase where you're just asking yourself, okay, what I'm trying to do, what we're trying to solve, what is the state of research for that task. For sentiment analysis, you can look at benchmarks, for instance. Get a clear view of what you're going to do. Get a clear view on the data you're going to use. Can you use model data sets that are already there? Are you going to collect more data? Are you going to need to label it? Do you need experts to label the data? Things like that. Then, when you have a good idea of what your data looks like, you can do a data analysis at this step as well. You're going to use model, and we should put an S there if you are doing Ansible modeling. You're going to look at models and what they can offer you in terms of performance, what's the accuracy, test them. And finally, you're going to deploy it. Well, usually in big corporations, the data scientist doesn't do that step, but it's important to know that it's there, and you have your role to play in there. So please try to interest yourself to that step too. And one thing you can do first in experiments, where your work, where you're mostly going to work when you're trying new models and processing your data, is to use experiment trackers. There's the most famous one is called Carbon. And basically it will help you, give you it's that easy to implement it. You just create a tracker and you say start and stop, and between those two trackers, you can put your code, and it will track on your device the energy consumption and the carbon impact only of your model, of your processing, and then you just have created a new metric. You can now measure the accuracy of your model, but you can also measure the environmental impact, and you can take decisions based on that. If you have two models, you don't know which one to choose. One is, I don't know, 0.89 accuracy. The other one is 0.91 accuracy. So basically the same in production. In benchmarks, it makes a difference, but in production, it's the same. Well, if there is a 10%, 50% difference in the environmental metrics, just choose the one that has the lowest impact. That's a way you can decide on equivalent models. You can choose the one that has a smaller footprint. And finally, if I zoom back again to that ML project lifecycle thing, we saw code Carbon that could be in the modeling phase as well as the data phase, depending on what you do and if you have intensive processing. And other things you can do, and that's the time where I promote a little bit about Boavizta. We are making tools to help you compute carbon intensities, but not only. You can have other factors, other impacts, as I explained before in the beginning of the presentation. We have an API and a front for this API where you can describe the hardware you're going to use, how long, what's the workload you're going to what typical workload you're going to have, and you can get estimations forward before starting your project. You can get an idea of what's going to be the emissions using that hardware. And at the end of the loop, you can monitor your infrastructure and the server where your model is going to run using Scaphandr, which is made by Hublot. And it's very close from Boavizta, as all members are in Boavizta. And also use BoAgent to both extract the hardware of the machine, the underlying machine, what's the CPU, what's the GPU, and extract the energy consumption from software sensors, and just keep track of the usage of your model that way and the energy you're going to use that way. And that's it for the like the explanations of what's the impact of AI, how to reduce it. I just want to add some few more words about it. We have seen some techniques that I encourage you to look at. I've put some papers down the slides, and I think you're going to get them at the end of the course. So don't hesitate to read the papers and explore the subject. But one thing that is important, everything that I have explained is useless if you use AI for something that emits a lot of carbon emissions, for instance. if you're training models to I don't know, search oil in the deep ocean, well, you have a pretty big indirect impact that you're going to help extract more oil from the earth and burn it and then emit more carbon. So in the end, just you can ask yourself the question, why you are using AI and how you're using it. Is it for good for the environment? Is it the good for society, social good? Or if it's just a questionable application. That's for the indirect impacts. And there is also the rebound effects that I haven't talked about, which are also very important to track. Rebound effects is basically when you have a process and you have optimized it very well. Take for instance the car. First cars, they were like made of what we had at the time in wood and with they were very slow. We couldn't do very long distance travels, but now today's we have increased the distance travel. We've increased the safety. It's easier to move with a car. And what we have observed is that people tend to move more. They use more the car. They do more kilometers because we have increased the efficiency of cars. Well, that's the same for the model. In the end, if you have scoped your project and you've done all the optimizations, and you say, oh wow, it's so fast, it's so great to have a BERT model that works that fast in production. Well, try to not say, okay, it's super good. Maybe we can put a even bigger model because we're going to do the same optimizations, or not say, okay, we're going to use it for something else because it's so efficient. We haven't think about it before because it was heavy to put in place. Try to scope the project at the beginning and keep track of that very easy slope to go in. The rebound effects are very difficult to quantify and to detect at first. And finally, if you're interested in all the subjects I have covered, you can apply to join. It's not an application. You can just fill a form, and we will be happy to integrate you in the ML working group of Boavizta. We're still very few working on that. As I said, Boavizta is a non-profit that works to make commons, so open source license on data sets, methodologies, and tools. And there is a ML section where we focus on ML impacts in priority. Well, thank you for your attention. You can contact me with my email, samuel@rince.me, if you have questions or if you want to talk about Boavizta, for instance, or anything else. I'll be glad to answer you. Thank you.